Hey there! Today, we're diving into the story of numbers that for centuries, the smartest people on the planet all agreed they flat out shouldn't exist.
All right, let's just jump right in with a question that feels like a trick. What is the square root of -1? I mean, what number times itself gives you -1? For literally most of history, the answer was simple. There isn't one. It's impossible. But the story of why mathematicians were forced to invent one? Well, it's an incredible tale of rivalry, secrets, and a revolution in how we see the entire world.
So, to really get why the square root of a negative number was so completely bizarre, we've got to rewind a bit and talk about an idea that seems even simpler: negative numbers themselves. You know, for most of human history, numbers were, they were things you could count. They were tied directly to the physical world. You have one cucumber, I give you another, you have two cucumbers. Makes perfect sense. It's simple, it's intuitive, it's real. But this is where things get weird. What in the world is a negative cucumber? How can you possibly have less than nothing of something you can hold in your hand? It feels like a ridiculous question, because for a very, very long time, it was.
And look, this wasn't some ancient confusion that people figured out quickly. Get this. As late as 1758, a respected mathematician named Francis Mazares was still calling negative numbers a concept that darkens the very whole doctrines of the equations. Basically, he thought they were nonsense that just made math confusing.
Okay, so if just plain old negative numbers were already making people's heads spin, you can imagine how they felt about taking the square root of 1. I mean, think about it. A positive times a positive is positive. A negative times a negative is also positive. So there was just no real number out there that could possibly do the job. It was a dead end, a mathematical absurdity. Right, so everyone was basically content to just shove these impossible numbers into a closet and forget about them, until a high-stakes, high-drama problem in Renaissance Italy made that completely impossible. The race was on to solve the cubic equation. Okay, so you gotta understand, there are two ways to solve an equation. You can just guess and check numbers until something works. That's trial and error. It's slow. But what mathematicians were truly after was a general formula, a single, powerful recipe that could solve any cubic equation you could think of. That was the holy grail, the master key. And this is where the story gets wild. I mean, this isn't some boring academic discovery. First, a guy named Alfaro finds a secret formula and only tells his student. Then, that student challenges another brilliant mathematician, Tartaglia, to a public math duel. Tartaglia, not wanting to be humiliated, figures out the secret himself and wins. But he keeps it secret too, until another guy, Cardano, makes him swear a sacred oath not to tell anyone. And then Cardano immediately turns around and publishes it for the whole world to see. It's pure drama. But here's the twist. Cardano publishes the secret, breaks his oath, and boom! He runs smack into a paradox. His amazing world-changing formula had a massive, troubling flaw. This was the maddening part. For some equations, Cardano knew for a fact that the answer was a simple real number, like, say, 4. But his own formula, the steps to get to that answer, forced him to work with the square root of a negative number along the way. The math in the middle was complete nonsense, but the answer at the end was perfectly correct. He was so frustrated, he just called the whole process useless. And then along comes our hero, Raphael Bombelli. He looks at Cardano's useless method and has this incredible thought. Instead of throwing it out because one step looks impossible, what if we just lean into it? What if we pretend this weird number is real, just for a second, and see where the path leads? So this was the genius move. Bombelli showed that you could use this impossible number as a kind of temporary stepping stone. You'd do your calculations, you'd follow the rules of algebra, and then, like magic, at the very end, these strange, imaginary parts would cancel each other out and just disappear, leaving you with the right, real-world answer. It was a fiction, sure, but it was an incredibly useful one.
So fast forward a bit, and this useful fiction finally gets a name, courtesy of René Descartes. He is the one who called it imaginary, and the name stuck. Today, we just call it I. And its most important superpower is right there. I squared equals -1. The impossible was now officially part of the system.
Okay, so these things exist now. They have a name, but where are they? If they don't live on the good old-fashioned number line with all the other numbers, where in the world do you put them? Think about it. Real numbers, they all fit neatly on a line. right? You can go left for negative, right for positive. But a number like 3 plus 2i, what we call a complex number, it has two parts. It's got the real part, the 3, and the imaginary part, the 2i. There's just not enough room for it on a single line. And this right here is the brilliant solution. We need another dimension. Welcome to the complex plane. The horizontal line is the same old real number line we know and love, but now we add a vertical line for the imaginary numbers. And just like that, every single complex number has its own unique address, its own spot on the map. It gave these abstract ideas a real geometric home. And this is where the story, I think, just gets absolutely mind-blowing. Because this number, a number born from a math duel and literally called imaginary, it turned out to be the perfect, essential language for describing the very real world that we all live in. Just think for a second about how much of our world is all about waves. Sound travels in waves. Light is an electromagnetic wave. Your phone gets signals through waves. Even the fabric of reality itself, according to quantum mechanics, is fundamentally wave-like. All of these things are described by sine and cosine functions. But here's the catch for engineers and physicists. The math behind waves, sines and cosines, it can be a nightmare. It is super complicated to work with. On the other hand, there's this other kind of math, exponential math, that's incredibly simple and clean. If only there was some way to connect the complicated world of waves to the easy world of exponentials. And then you get this, Euler's identity. People call it the most beautiful equation in all of mathematics, and you can see why. It connects the 5 most important numbers in math, e, pi, 1, 0, and it does it with our number, I. This equation is that magic bridge. It's the Rosetta Stone that connects waves and circles to the simple, beautiful world of exponentials. So this gives engineers an incredible new playbook, right? Here's how it works. You start with a really hard real-world problem with waves. Then, you use Euler's formula to hop over into the complex world. There, the math becomes super easy, so you solve it. And then you just hop back to the real world with the correct answer. The imaginary world becomes this amazing, powerful shortcut. And this is not just some abstract math trick. This is the bedrock of our modern world. Your phone, the Wi-Fi you're probably using right now, the electrical grid powering your house, the science of quantum mechanics, all of it is designed, analyzed, and understood using the math of complex numbers. That number that doesn't exist is woven into the very fabric of our lives. Which brings us to this one last kind of wild thought to leave you with. A number that we invented out of pure mathematical need, a number that we literally labeled imaginary, turns out to be one of the best ways we have to describe physical reality. So, what does that say about the nature of reality itself? Something to chew on. Thanks for joining me.